Hello everyone, Henry here. Before we jump into the review, I want to bring to your attention that this very helpful review was brought to you by Professor Campbell. While Professor Campbell does do a very comprehensive review of mechanics, please do know that she is not your teacher and she may have emphasized certain topics that your teacher did not focus on. She may also have missed out specific materials covered by your own professor. Similarly, there are always discrepancy between classes, so to be safe, please consult your own teachers for any questions or concerns regarding the exam. Additionally, Professor Campbell do state that the exam is open book, but please consult your professor to make sure that you're using the authorized materials. And with the boring stuff out of the way, enjoy your cramming podcast.
Okay, hello students of mechanics. This is your mechanics study podcast I've been asked to do for you. What I'm going to do is just kind of take you through an overview of the main topics that we cover in this course, just addressing, a few big ideas, a few common misconceptions, a few reminders. So that's the game plan. So when I teach this course, I split it up into 9 sections, which I call modules. If you didn't take the course with me, then the structure might be a little different. However, the topic that I'll talk about they're going to be the same. So the first topic that we cover in this course is, vectors. And part of that is also a math review. So obviously, in order to do well in this class, you need to be able to use your math toolkit for, relevant problems. You need to be able to do unit conversion, you need to be able to add vectors, that sort of thing. You're not going to be test explicitly on these things, but of course, in order to demonstrate a full solution to a lot of these problems, you're going to need to be able to do that. So that's the first topic. Second topic, kinematics, but more specifically, kinematics graphing. Can you look at a position time graph, velocity time graph, acceleration time graph, and be able to tell me key information from those graphs? So can you read them, and also can you draw them? Can you go from an acceleration time graph to a velocity time graph to a position time graph? Can you go the other way? Can you go from a position time graph to a velocity time graph to an acceleration time graph? So being able to do that obviously is very important. A couple things that I'll just remind you is the importance of knowing what negative acceleration means. So this is a very common mistake students make. So note that negative acceleration is not the same as an object slowing down. If the object is moving in the positive x direction, then yes, negative acceleration is slowing down, but it also depends on the direction of your motion. So for example, in the positive direction, it's what we'd expect. Positive acceleration is speeding up and negative acceleration is slowing down. If you're moving in the negative x direction, it's actually the opposite. So if you're moving in the negative x direction, a positive acceleration will actually be slowing you down, right? Kind of like working against you in the negative direction. And a negative acceleration will actually be speeding you up. So you can kind of think about this in terms of gravity, right? Gravity is minus 9.8 meters per second squared. That's a negative acceleration. When the ball is traveling upward, which by convention we choose to be positive, I know that the object will be slowing down. Then as it starts falling, moving in the negative direction, it will be speeding up. So think about a projectile as a way to remember this, or just, jot it down off to the side, the convention and the relationship between the signs. Okay, so that's important to keep in mind. Obviously, this shows up on your position time graph, right? So if a position time graph is concave up, that means it has positive acceleration. If it's concave down, that means that it has negative acceleration. So also, another thing to note is, what does negative velocity mean? What does it mean to be moving at minus 2 meters per second? So remember that negative velocity, all it is, it's saying that the object is moving in the negative direction. So note also, and this is another common misconception, what a positive slope on a velocity time graph means. This doesn't always mean that the object is speeding up. So obviously that will depend on the sign. So if you're in moving with a negative velocity, but your velocity time graph has a positive slope, that means that the velocity is going to be getting less and less negative, so you're actually going to be slowing down. After it crosses the x-axis, so v equals 0, and if it's still moving in the positive direction, it will be speeding up. So of course, there's some subtleties hidden in the signs of these graphs. So make sure you're comfortable with doing that. Obviously, what we're looking for in a graphing problem, if you're drawing a graph, we want it to be really neat. We want it to be labeled. We want it to be really clear as to when objects are speeding up and slowing down, but also, not putting big dramatic jumps in the graph that don't need to be there. So that's kind of more or less what you need to know for kinematics graphing problems. And the third topic is just straight up kinematics. So of course, you've done two types of kinematics, one-dimensional kinematics and two-dimensional kinematics. So you obviously will need to know the kinematics equations. Of course, since this is an exam where you can use your own resources, make sure that the kinematic equations are handy, because obviously you're going to be required to use those. It's important to have a good strategy to do a problem, knowing what equations to use, splitting up your information into what's happening in the x direction and what's happening in the y direction, of course, relevant to two-dimensional motion. A reminder about the definition of the acceleration due to gravity. So AY for a projectile motion problem is going to be minus g, minus 9.8 meters per second squared. So another reminder that g itself as a constant is positive 9.8 meters per second squared. But the sign comes from the typical sign convention where down is negative y. Okay, so for a projectile motion problem, some key things you're going to need to be able to split up your initial velocity vector into its x and y components. Again, going to need to be able to work in those x and y components. Often the thing that connects those is going to be the time, right? The time is the same in x and y. And then, of course, solving for whatever quantity you're being asked for. Something that's very important at the very top of a projectile's motion, there is going to be an instant where the object's velocity in the y direction is 0. Okay, so this happens at its maximum height. Of course, this doesn't mean that the object stops. In one-dimensional motion, the object stops, but in two-dimensional motion, remember, since there's no acceleration in the x direction, the speed in the x direction or velocity even, is going to be the same the entire time. So it's still going to be moving in the positive x direction, but just in the y direction, it will momentarily stop at the top of its trajectory. Okay, so that's kinematics. The next big topic that we cover is forces. So forces is obviously a lot kind of involved in a forces problem. You need to make sure you have a free body diagram, right? Your object is represented by a point and your arrows come out from that point. You need to make sure you set up a coordinate system so you know how to define the signs of your forces and the signs of your, say, acceleration, that sort of thing. Free body diagram, coordinate system, and then you can apply Newton's second law. So you can do the sum of the forces in the x direction, the sum of the forces in the y direction, right? Set them both equal to mass times acceleration. Obviously, in all the questions we've done, there's either going to be an acceleration in the x direction or an acceleration in the y direction, but not both. Okay, so typically, in a lot of the problems we've done, the acceleration in the y direction is 0 because the object is not moving up or down, like in and out of the floor, for example, but that's not necessarily a rule. There could be motion in the y direction. A good example of that is an elevator problem. So, at that point, you then need to solve for whatever your unknown is using Newton's second law, the equations that you get from it. Sometimes this will be a systems of equations. Sometimes this will be a simple solving problem. And that's basically it. So something that is a couple things that are important. Remember that if the net force is equal to 0, this means this could mean a couple of things. This is called equilibrium. And there's two ways that you can be in equilibrium. You could be not moving at all, or you could be moving at a constant speed, right? A is equal to 0, either way. Remember that the net force being equal to 0 doesn't necessarily mean there are no forces acting on the object, right? It just means that the sum of the forces is equal to 0. I also want to use this opportunity to stress the difference between static and kinetic friction, right? We know static is the friction of objects at rest. Kinetic friction is the friction of objects that are moving. So the static friction always is going to be exactly as much as it needs to be in order to keep the object at rest until you get to its maximum static friction. And that's what you use the equation μs times n for, to calculate that maximum. After that, if the object is, the sum of the forces is that the static friction is being maxed out, after that, the object is going to start to move. And instead of static friction, you have kinetic friction. So, of course, the coefficient of kinetic friction is going to be less than the coefficient of static friction, because generally it takes more to get an object moving than to keep it moving, which, if you've ever tried to get a running start at, a hill, say. Okay. So that's basically it. This is generally to the point where, students are generally more comfortable with the material because it clicks really well with what they've done and seen before in high school. Once we get to the next topic, Newton's third law, we kind of get away from that a little bit. So Newton's third law, topic 5, most important thing is, the definition. Every action has an equal and opposite reaction. What does that mean? For every force, there's an equal and opposite force. And I know a few specific things about that. These, what we call action-reaction pairs, so these pair of forces, we know that they have to be acting on different objects. Also, they have to be the same sort of force, the same kind of force. So a really common misconception that I see students do a lot is label the normal force and the gravity as an action-reaction pair, because you say, well, in this, they're the same in magnitude and opposite in direction. It's true that, and if it's just an object sitting on a table, that the normal force and the gravitational force are equal and opposite. That doesn't necessarily make them an action-reaction pair. So for one thing, normal force is a contact force. Fg is, it's the gravitational force. So the action-reaction pair for gravity is actually it also needs to be gravity. So the gravitational pull of the Earth on a book is the same as the gravitational pull of the book on the Earth. Okay? And of course, we don't see this acceleration really because the book's mass is so much smaller than the mass of the Earth. So that's why the Earth is not rushing up to meet us, and or sometimes it feels that way. I guess it's relative. So a common misconception on different objects, same kind of force, very important. So on a third law problem, you need to label your action-reaction pairs, indicate them. You're going to need a free body diagram separately for each object that's involved in your system. You need to obviously label the coordinate system. You might choose for a different coordinate system for each object, or you might choose the same one. It's up to you as long as you're consistent with it. You also need to link the acceleration. So if the objects are connected, you can say that they're moving together and the magnitudes of the accelerations are going to be the same. Okay, and then you end up solving for any missing quantities. Typically, this will end up being a systems of equations, solving for the acceleration and the tension if there is an acceleration. So that's Newton's third law in a nutshell. Topic 6 that I have here is circular motion, and usually this is a bit of a stumbling block for students. It's tricky because you need to think in a new coordinate system. So instead of the XYZ, you're thinking in RTZ. So R is the direction towards the center of the circle that you're dealing with in circular motion. So obviously it's really important to identify the circle. It sounds silly, but identifying the circle in circular motion so that you know which way your R direction is. Really, R is the most important to figure out. Then T is the direction that's tangent to the circle. Z is the direction that's perpendicular to the circle. The centripetal acceleration, AC, we have a special equation for that. It's V squared over R. The centripetal acceleration for circular motion is never going to be zero, right? Even though the object isn't moving in or out of the circle, I know that the direction is always changing. So there's always going to be an acceleration, and it's always going to be V squared over R in the R direction. So that's one of the big equations: acceleration, direction towards the center of the circle. V for circular motion, the speed of the object as it travels around the circle is going to be equal to 2 pi r over t, where t is the period. T is the amount of time that it takes to make one full revolution of the circle. Of course, we also have a special equation for gravity, which depends on the gravitational constant, capital G. Also depends on the two masses involved divided by the radius squared. So, have that equation in your back pocket as well. So for any circular motion problems, again, you're gonna do a free, the setup is gonna be the same as a force problem. You're gonna do a free body diagram. Be really clear as to what your R direction is, and make sure that you're very clearly identified the force that is your centripetal force. So again, the centripetal force isn't a force in and of itself. It's going to be some other force. It's going to be tension or the normal force or friction. So identifying what force that is, and then you set that, some of the forces in the R direction is equal to mv squared over R. Sometimes you'll also need to do the sum of the forces in the Z direction to solve for, say, normal force or what have you. But yeah, so super important. Set it equal to mv squared over R, and solve for your missing quantity. Okay, so that's circular motion in a nutshell, right? Being able to do, knowing the free body diagrams for both a vertical circle and a horizontal circle, super important. So again, circular motion may be the trickiest topic in this course, but the actual computation you need to do with circular motion is fairly straightforward. It's always in the setup. So that's topic 6. Topic 7, a little bit shorter topic, thank goodness, is work. So for work, what are you going to need to know? You should know probably the definition of the dot product, right? How do you calculate the dot product? You have 2 different definitions, right? One with multiplying the x components plus the y components plus the z components together and coming up with a sum. Remember that the dot product or the scalar product should always give you a scalar quantity. Okay, so you shouldn't get a vector out of this. It's just going to be a number with units. Don't forget your units. All right, that's true everywhere in this course. Obviously, don't forget your units. And also don't forget to identify vectors as vectors and scalars as scalars, right? By now you should know if I asked you for the velocity, I'm asking you for a vector. If I asked you for the speed, I'm asking you for a scalar. So things like that. Obviously very important to keep in mind. So work is a scalar, so it needs units and no direction because it's a scalar. Note that we have the other definition of work, that is the magnitude of the force times the magnitude of the displacement times cosine of the angle between them. That means that if F and D are pointing in different directions, or say in opposite direction, the work done is going to be negative. So negative work is a possibility. So the work is only done by the bit of the force that's acting in the same direction as the displacement, right? That's what the cos theta does, is it just chunks that force, takes a part of it that's in the same direction as the displacement vector. We also know of the work energy theorem. So the net work on a system is going to be the change in kinetic energy delta K. So the final takeaway, the initial, that's a really nice way to find, a final speed without using, say, kinematics. So one thing I will note, especially going into, the next topic is energy, is that in some of these problems, there are going to be multiple ways to solve them, right? You might be able to solve a problem either using forces or energy. And unless we specify, which, is fairly unlikely, you can use whatever method you want. And sometimes that is a good thing because it gives you options. Sometimes it's a bad thing because sometimes it's easier when there's only one way to do things. So just that being said. Okay, so that's work in a nutshell. Obviously, that is very closely connected to energy. So that's topic 8. There are different types of energy, right, that we work with explicitly. So gravitational potential, UG is equal to mgh, that one. Elastic potential, US is equal to 1/2 kx squared, right? We know these equations. You should have them handy. You probably know them by now. They're not that hard, so you probably do. And finally, the kinetic energy is 1/2 mv squared, right? So you need to know those. You need to know that the change in thermal energy is minus the work done by friction. So obviously, we know that the work done by friction is going to end up being negative. Yeah, typically, I guess always, because it's always going to be opposing in the opposite direction as the displacement. Right, know that definition. Obviously, make sure that when you're setting up your conservation of energy, that you are paying close attention to the signs, right? Make sure that they line up, right? If delta E thermal is negative work done by friction, but work done by friction is negative as well, then you're going to have a double negative. So delta E thermal is going to be positive because it's adding heat to the system. So you should also know the difference between conservative and non-conservative forces, right? Conservative forces conserve mechanical energy. So remember the definition of mechanical energy too, which is K plus US plus UG. We also, obviously energy conservation is a big part of this course. So you have the big equation, maybe this is the one you use, delta K plus delta UG plus delta US plus delta E thermal is equal to the work done by external forces. So you need to be able to use that, right? Initial is equal to final. It's obviously important in these problems to choose a system because the system choice is going to define how you talk about gravity. I'm sorry, not gravity, but friction, try friction. What you need to do is identify your system so that, if it includes the surface, then your work done by friction is going to be internal. So you're going to have a delta E thermal. If you don't include your surface, then friction is going to be external. So you're going to count the work done by friction as work external work. So in an energy conservation problem, you're going to need to also define what your initial and final state is, right? Is your initial state when the ball is at the top of the hill, or when the ball is at the bottom of the hill, or when the ball is at the top of the second hill, right? You need to identify what two states you're comparing when you're doing energy conservation. Obviously for us as your teachers as they mark your exam, but also for you, so you know exactly what you're talking about and you don't accidentally throw in extra energies that aren't there. Okay, so a common mistake I see, an object going from rest to rest, and that at some point to get to from point A to point B, it needs to have gained kinetic energy. So you throw in kinetic energy in your equation somewhere because it has some at some point. But since it goes from rest to rest, your delta kinetic energy is actually going to be 0. So even though it had kinetic energy at some point through its path, we don't need to include it in our conservation of energy equation. Also, if you do have friction in an energy problem, you need to identify, you need to set up a work problem, right? Calculating the work done by friction, you're going to need a little free body diagram. You should show me doing the dot product. And of course, like in a lot of the scenarios that we've seen with work done by friction, I think there's only a few different ones that we've seen, but just showing me that just a little bit of work, showing me the dot product is basically all you need to do. If it's on a flat surface, right, that's easy money, right? You know how to calculate the work done by friction on a flat surface, okay? So take advantage of that. Okay, finally, the last topic, the one squished in at the end of the course, is momentum. So we have two definitions of momentum. So P is equal to mv. Of course, momentum is going to be a vector, right, because it's a scalar mass times a vector velocity. And we also have that the force is equal to the change of momentum over the change in t, right? This is the change in t over which the force was applied. We know that another thing is that momentum is conserved, in an isolated system. So the initial momentum is equal to the final momentum. So this we can use in every sort of collision that we have. In most collisions, though, technically in every collision, energy is not going to be conserved. There are situations, and there's different ways to talk about it. I call it a perfectly elastic collision where energy is conserved as well as momentum, and you can set that up, both an energy and a momentum problem for the same collision. And then again, usually you'll end up with a systems of equations, which is a really fun, long problem. However, your teacher's, definitions of what is elastic, what is perfectly elastic, what is inelastic might be a little bit different. So I'll shy away from using that terminology, but just know that momentum is always going to be conserved and energy might be conserved, but it's only conserved when we tell you it's conserved. Okay, so don't assume that energy is conserved in a collision. Note that we have different kinds of what we call collisions too. An inverse collision would be an explosion, right? The object starts from rest and then breaks apart into multiple pieces, right? Momentum is conserved in that case. We also have the situation where you have two objects and they collide and they bounce off of each other, right? We also have the situation where two objects collide and they stick together. Okay, so that the final mass, they end up moving together, and their final mass is going to be the sum of the masses, right? So, okay, I guess that's it for the topics of the course. Just a few little studying tips just to end this. I guess the first one would be when you are practicing. So, we have a review package for you. When you are solving the review package, I recommend that you take chunks of it and write it like you would a test. So set aside so much time for yourself. Do as much as you can. Don't look at the solution and see how you do. And I would recommend even, when you're done the time, I would spend a little bit more time looking over it and thinking about it without looking at the solution before finally going to the solution and figuring out, okay, this is what I made this little mistake. This is what I didn't know how to do, right? But when you're doing this, don't open the solution right away. Because, if you were to practice what a test is like, we obviously don't give you the solution to the test. So, working with the solution book in preparation for the test is not preparing yourself for what the test is going to be like, right? Let yourself struggle. Let yourself not know for a while. Maybe even try asking your teachers before referring to the solution. I might ask you if you look at the solution, but if you said no, I'm trying to do it without, then that's great, and I'm happy to help you. That's in a way that's not just telling you to look at the solution. Okay, so do your best to stay away from the solution for the beginning until you finally actually need it and finally want to look at it. I highly recommend that you make yourself a formula sheet. And obviously there's one that's provided, this one that goes with the course. But I highly recommend instead, since this is, quote unquote, open book, make one for yourself. This is an excellent way to study because it helps you identify what things are important. And it also, I would recommend if you do this to make the study sheet soon. Make it before you start studying. So if you come across something and you're like, oh, I actually need this equation that I forgot that I needed, then you can add it to your study sheet. And also by the time you get to the exam, you're used to doing questions with your study sheet. Yeah, so if you do that, do it soon. Finally, my advice is, obviously, y'all are busy, you have lots of other exams. I recommend against, crazy cramming sessions right at the last minute. I highly recommend things like getting a really good sleep right before. Even I remember, like, in grad school, my supervisor told me the night before, like, my big presentation of my dissertation, he told me to go to the movies. Okay, so I mean, I'm not telling you to slack off studying, but I do want to say, just, maybe review a few things the night before, and then get a good night's sleep, watch a good show, go for a walk, and yeah, obviously looking after yourself. It's really hard to do physics when you're exhausted. Okay, eat a good meal before, have some snacks ready, and yeah, I mean, I guess that's all of my advice. I want to wish you the best of luck in your studying, and feel free to stop by any of the mechanics teachers' office hours or message your teacher if you need any help with anything. So have a good day and take care.